All right, geometers, we are so almost done. On today's show, we take a look at the one transformation that you studied in high school that we haven't talked about yet. So let's talk about a similarity transformation. A similarity transformation has a proportionality constant R for ratio. It's a bijection from the set of points in the plane to the set of points in the plane, such that for any 2 points A and B with those images, the distance between the images is R times the distance between the original 2 points. So a similarity transformation is a composition of transformations, at least one of which is a dilation. The dilation that you're familiar with, centered at a point O with proportionality constant R, that dilation is a similarity transformation. The thing you're familiar with from high school has to be one of the transformations in the mix when you come up with a similarity transformation. So what gets preserved under similarity transformations? Well, that's the list of things that got preserved under isometries. Are they preserved under similarity transformations? Well, yes. Segments go to segments, but we don't have congruence of segments. Lines stay lines. If a ray was between two other rays before, it's between two other rays after. Angle measures are preserved. The image of a triangle is a triangle, but a similar triangle. Circles, the image of a circle is a circle, but with different radius, and area would not be preserved in a similarity transformation. Can similarity transformations be composed? Sure they can. If you do a composition of two similarity transformations, and this one has a proportionality constant of little r, and this one has a proportionality constant of little s, then S composed with R has a proportionality constant R times S. That's great. Does the inverse of a similarity transformation exist? Sure it does. It has proportionality constant 1 over R, and it is a similarity transformation. Thing to think about here, you have triangle ego, and you have triangle ego prime, so to speak, E prime, G prime, O. This is the image of that after a dilation. Where's the center of the dilation? Hit the pause button. Think about where the center of the dilation is. Hit the pause button. Well, we know that E and E prime are collinear with the center of the dilation, and we know that G and G prime are collinear with the center of the dilation, and we know that O and O prime are, oh golly, collinear with the center of the dilation, and so this point P is the center of the dilation. What's R? R is PE prime over PE, or if you like, PG prime over PG, or if you like, PO prime over PO. It doesn't matter. Those ratios are the same, and it gives us a method to find centers of dilations. You should take some time with a GeoGebra or Geometer Sketchpad or Cabri or some program and play with dilations just to see the properties, but these are the basics. So there.